Pluto made them come all along. It was like it was never actually a section of the nearby planetary group's planetary progressive system. Pluto's circle crosses that of another planet, and that is no sort of conduct for a planet. Pluto, the baffling smaller dwarf planet at the edge of our planetary group, is creating a ruckus in the galactic local area. Late reports suggest an approaching crash with Neptune, igniting concerns among scientists and space lovers alike. Prestigious specialists, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about the potential results of this celestial conflict. But how exactly did Pluto find itself on a crash course with its far-off neighbor? And what could this grandiose crash mean for our world on Earth? Join us as we dig into the startling situation developing between Pluto and Neptune. The peculiarities of Pluto's orbit. Pluto, once viewed as an undeniable planet, was later reclassified as a dwarf planet due to its remarkable orbit. Nonetheless, this change has not stopped it from continuing to captivate and draw in the cosmic community. Recent forecasts from unmistakable researchers, including Neil deGrasse Tyson and Michio Kaku, have highlighted an unsettling closeness between Pluto's trajectory and that of Neptune. These specialists are warning about a potential impact between the two planets, representing a critical danger to Earth. The peculiarity of Pluto's venture around the Sun lies in its unique characteristics within our nearby planetary group. Its orbit spans a broad 248.8 years, and since its discovery in 1930, Pluto has not completed a full revolution. What adds to its intrigue is the exceptionally elliptical nature of its orbit, a departure from the nearly circular orbits of the major planets. Moreover, Pluto's orbit is marked by a 17 degrees tilt to the ecliptic plane, making its path steeper compared to other planets. This mix of tilt and eccentricity presents layers of complexity to Pluto's orbital pattern. A remarkable part of Pluto's orbit lies in its crossing point with Neptune's path. For roughly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions about their respective positions in the solar system. The gravitational safeguards. The explanation lies in the gravitational influences exerted by other planets. Assessing Pluto's orbit began shortly after its discovery, presenting an astonishing challenge for cosmologists. Unlike most planets whose orbits align relatively close to the ecliptic plane, Pluto's unique features a steep tilt and an elliptical shape make it an anomaly. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. However, the stability of Pluto's orbit amidst these complexities serves as evidence of the intricate mechanics of space. The three-body problem in space involves understanding the motion and gravitational interactions among three celestial bodies such as Pluto, Neptune, and the Sun. It is akin to predicting their paths based on initial positions and mutual gravitational influences. For Pluto's situation, this problem explains the delicate balance between its orbit, Neptune's orbit, and the Sun's gravitational pull. Several mechanisms help maintain this stability. Asymmetric libration. This phenomenon ensures that when Pluto crosses Neptune's orbit, it is situated at least 90 degrees away from Neptune, preventing potential collisions. Scope libration. This refers to the vertical movement of a celestial body in its orbit. It ensures that when Pluto approaches Neptune, it is positioned significantly above Neptune's orbital plane, providing an additional layer of protection. VZK oscillation. Named after three researchers von Zippel-Lasker and Kolshevnikov, this oscillation helps explain why Pluto's orbit remains chaotic yet stable over time. The role of giant planets. Mathematical simulations in the late 1980s revealed that despite its chaotic properties, Pluto's orbit is actually stable. Even minor initial deviations can lead to significant changes over millions of years, yet Pluto's orbit maintains its integrity over long timescales. Recent computer simulations have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn affect Pluto's path. One crucial factor is Neptune's special resonance, where it completes 3 orbits for every 2 of Pluto's. This resonance contributes to Pluto's long-term stability. Jupiter's gravity plays a significant role in stabilizing Pluto's path. Saturn has a smaller effect but still contributes to maintaining Pluto's position in space. These factors ensure Pluto's safe and stable movement through space for billions of years. Without these interactions, the solar system would be far more chaotic, potentially leading to planetary collisions or ejections. The possibility of a Pluto-Neptune collision. Despite these stabilizing forces, prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have recently expressed concerns about a possible collision between Pluto and Neptune. This raises the question: Neil deGrasse Tyson, known for making astronomy accessible to the public, has studied Pluto extensively. He suggests that the three-body problem could pose a real danger, indicating that a collision with Neptune may be long overdue. He warns that such an event could disrupt the balance of the solar system, with catastrophic consequences potentially affecting Earth. If Pluto and Neptune were to collide, the impact would be extraordinary and devastating. Pluto, being smaller and composed mostly of ice, would likely break apart. Debris from the collision could scatter across the solar system, potentially impacting other celestial bodies. Neptune's orbit could be altered, causing ripple effects throughout the outer solar system. Michio Kaku, a renowned theoretical physicist, offers a different perspective. He believes that studying Pluto's complex gravitational interactions can provide valuable lessons for future space exploration. Understanding Pluto's orbit could help scientists predict potential dangers and navigate the solar system more effectively. Kaku also connects the Pluto-Neptune scenario to string theory, a framework that seeks to describe the fundamental forces of the universe. A collision of this scale could generate gravitational waves, providing new insights into the nature of spacetime. The bigger picture. Pluto's orbit serves as a striking illustration of celestial mechanics, showcasing the delicate balance between chaos and stability. The three-body problem reminds us that the universe is full of mysteries waiting to be unraveled. While planetary collisions are extremely rare, they are not impossible. Other potential disruptions include rogue planets. These drifting planets, ejected from their original star systems, could theoretically enter another system and cause chaos. Galaxy mergers. During these massive cosmic events, star systems can be thrown into disarray, altering planetary orbits or even ejecting planets into interstellar space. Although the vastness of space makes direct planetary collisions rare, ongoing research helps us better understand the intricate dynamics of celestial motion. Final thoughts. The concerns raised by astrophysicists about a possible Pluto-Neptune collision highlight the dynamic and ever-changing nature of the cosmos. Whether or not such an event will occur remains uncertain. However, the study of Pluto's orbit and its interactions with other celestial bodies continues to provide valuable insights into the mechanics of our solar system. As our understanding of space evolves, one thing remains clear: there is still so much more to discover. The long-term stability of Pluto's orbit. Despite the concerns raised by astrophysicists, the question remains: is a collision between Pluto and Neptune truly imminent? The mathematical models and simulations that have been conducted for decades suggest that Pluto's orbit remains stable due to its unique resonances with Neptune. The 3:2 orbital resonance ensures that Pluto never comes dangerously close to Neptune. This means that even though Pluto's orbit crosses Neptune's path, the two bodies are never in the same place at the same time. However, the three-body problem introduces uncertainties. While current models suggest stability, even minor gravitational perturbations such as an undetected passing asteroid or the influence of a distant celestial body could introduce changes in Pluto's trajectory over millions of years. The impact of an unstable Pluto-Neptune system. If hypothetically an external force were to disrupt the gravitational equilibrium maintaining Pluto's orbit, the consequences could extend far beyond just Pluto and Neptune. The domino effect could impact other planets in the solar system. Neptune's orbit disturbance. A deviation in Neptune's position could alter the gravitational balance of the entire outer solar system. Kuiper belt disruptions. Pluto resides within the Kuiper belt, a region filled with thousands of icy bodies and dwarf planets. A change in Pluto's trajectory could send objects careening toward the inner solar system, potentially endangering Earth. Effects on Jupiter and Saturn. As massive planets, Jupiter and Saturn have strong gravitational influences. A shift in Neptune's orbit could result in subtle but measurable variations in their positions over time. While these scenarios are speculative, they highlight the interconnected nature of celestial mechanics and the potential ripple effects of a major planetary event. The role of dark matter and undiscovered celestial forces. Another fascinating aspect of planetary motion is the potential influence of dark matter and other unknown cosmic forces. Could dark matter influence Pluto's orbit? While dark matter is largely undetectable, it interacts with gravity. Some researchers speculate that small concentrations of dark matter could be affecting the orbits of distant celestial bodies like Pluto. The search for Planet 9. Some astronomers believe there is an undiscovered ninth planet lurking in the outer solar system, exerting a gravitational pull on Pluto and other Kuiper belt objects. If such a planet exists, its presence could subtly alter Pluto's orbit over time. Although no concrete evidence supports these theories, ongoing research in astrophysics continues to explore the possibility of hidden forces shaping the solar system. The broader implications for space exploration. If a Pluto-Neptune collision were even remotely possible, it would raise serious concerns for future space exploration. Space agencies like NASA, ESA, and SpaceX are already planning missions to explore the outer solar system in greater detail. Pluto probes. Missions like New Horizons provided valuable insights into Pluto's surface and atmosphere. However, follow-up missions with orbital probes could help refine models of its trajectory. Neptune missions. Neptune remains one of the least explored planets in the solar system. A dedicated orbital mission could provide crucial data on its gravitational interactions with Pluto and other Kuiper Belt objects. Asteroid deflection technology. If we ever detect a real threat of planetary collisions, whether from Pluto asteroids or other celestial bodies, developing asteroid deflection technology could become a priority for planetary defense initiatives. The future of Pluto in our solar system. Despite the uncertainties, Pluto remains one of the most intriguing celestial bodies in the solar system. The renaming of Pluto as a dwarf planet sparked intense debate among scientists and the general public. Yet its complex orbit, unique interactions with Neptune, and the mysteries of its gravitational stability continue to captivate astronomers. Neil deGrasse Tyson and Michio Kaku both highlight Pluto's importance in understanding celestial mechanics. While Tyson sees Pluto's reclassification as a sign of evolving scientific understanding, Kaku views it as an opportunity to connect planetary science with theoretical physics and string theory. Even if Pluto never collides with Neptune, studying its chaotic yet stable orbit gives us deeper insights into the fundamental laws governing the universe.